Hello, everybody. My name is Sergey Samsonov, and I would like to present you our joint paper with Daniil Tsepkin, Alexey Naumov, and Eric Moulin on the finite sample analysis of the temporal difference learning. I will start with a brief recap on the setting of TD learning procedure. We consider the problem of estimating the value of a policy in a discounted MDP given by a certain tuple, where S and A are respectively state and action spaces. They are assumed to be complete metric spaces with their Borel sigma algebras. Gamma from 0 to 1 is a discount factor. P is the transition kernel related to the properties of our environment. Reward function R takes values from 0 to 1 and is deterministic. And the policy phi is a distribution over the action space A. And we aim to estimate the agent's value function, which is a discounted sum of the rewards collected by the agent if we assume that it follows some policy pi. We will consider TD learning in a setting of linear function approximation. That is, we will approximate the true value function v pi by its linear estimate with some fixed feature mapping phi. Main contributions of our paper are as follows. We propose a refined high probability error bound for TD learning with linear function approximation and Pollock Rupert averaging, equipped with universal and instance independent step size. And we do it both under generative model assumption and for the setting when the sequence of our learning tuples form a Markov chain. In order to do this, we provide refined error bounds for the general linear stochastic approximation algorithm by directly assuming the so-called exponential stability of the random matrix product. And then we present a novel proof of this exponential stability specifically for the setting of the TD learning algorithm. Our analysis is tighter than the previously available results in the literature and allows us to eliminate at the same time the need to do additional projection step when we consider high order error moments, and also to remove the scaling of the step size with the minimum eigenvalue of the feature matrix of the algorithm. So I will start with the part on the general linear stochastic approximation procedure. We aim to find the solution of the system of linear equation defined on the slide. Neither system matrix A bar nor the right-hand side B bar are available directly. However, they can be estimated based on noisy observations A of Z10, B of Z10, where Z10 is either a ID sequence or a Markov chain. Then the LSA algorithm is defined by the formula 2. We will consider the properties of the Pollock Rupert averaged estimate bar theta, equipped with size of burn-in, which is half of available observations. That is, we set n0, which is n over 2. In this case, we can define the noise variable epsilon, which measures the noise level of the problem measured at the optimal point theta star. And then we can make our first assumption, A1, which states that our sequence of random variables Zk are independent and identically distributed. They provide unbiased estimates of A bar and B bar, respectively. Moreover, we assume that the noise variables epsilon are uniformly bounded, as well as the random oracles A and centered version of A, respectively. Moreover, under this assumption, we can decompose the error of the nth iterate of the linear stochastic approximation into sum of two parts. The first one is the transient term theta n tilde transient, and the second one is the fluctuation term. And any analysis of the linear stochastic approximation algorithm is quite concerned about the properties of the first term. And for our analysis, we will follow the next scheme. We will directly assume the exponential stability property, which is defined on the slide as the assumption A2 of P, which stands that the P norm of our product of random matrices times any vector u from R set D is bounded by exponentially small term for any range of step sizes alpha from 0 to some stability threshold, which is referred to as alpha p infinity. Then we will directly check that the assumption A2 of P holds for the setting of TD0 algorithm. Under assumptions A1 and A2, we can provide the following P-moment bound on the error of the general linear stochastic approximation algorithm provided on the slide. It is in the formula 6. Note that here the leading term of the bound is affected by the additional multiplying factor 1 plus R1 of alpha. And this term R1 of alpha is generally not small, provided that we don't adjust the step size alpha with the factor A, which is a contracting factor in the product of random matrices. And this will be the reason of suboptimality of some variance counterparts of our bounds. Otherwise, the leading term is well adjusted with the central limit theorem for linear stochastic approximation algorithm. One can try to mitigate this problem if we either scale the step size alpha with the length of trajectory n, or if we consider the decreasing step size. However, this will yield the suboptimal reduction rate for the initial error norm of theta 0 minus theta star. So we will study properties of the constant step size algorithm alpha when alpha is not adjusted with the length of our trajectory n. So now we consider the specific setting of TD learning. So TD with linear function approximation can be written as a particular instance of the LSA algorithm with the design matrix A and right-hand side bar B defined on the slide, and the random oracles AK and BK defined in formula 8, respectively. In this case, we can show that the in this case, we need to assume the following properties of the design matrix sigma phi and the observations and the learning tuples. First, we assume that the learning tuples are generated IID with that is, we assume that the agent is available to resample the starting point after every iteration of the update of the estimate of V pi. Second, we will assume that the design matrix sigma phi defined on the slide is non-degenerate with minimum eigenvalue strictly larger than 0. We will also assume that the feature mapping phi of S is bounded by 1 in norm for any state S. In this case, it can be shown that theta star, which is the solution of the linear system defined on the previous slides, is also a solution of the weighted least squares problems, which is defined now. And then we can say that the previous results available in the literature allows us to obtain both the second moment or p-moment bounds for TD learning under different assumptions. However, available high probability bounds for TD0 procedure requires that the step size scales with the minimum eigenvalue of the matrix sigma phi from the previous slide. Alternatively, the study of Patil et al. Shows high probability bounds for projected TD0 iterates, where the projection procedure is based on the prior knowledge of the true solution norm theta star. We will show that our analysis is free from both of these drawbacks. The key element of our proof will be the fact that indeed, under assumptions TD1 and TD2, we are able to check the stability assumption A2 of P with constant small a, which is the contraction rate, which depends upon the properties of the feature matrix. So it scales as 1 minus gamma times lambda mean. But the stability threshold alpha p infinity, the maximum step size under which we have the stability of random matrix product, does not depend upon lambda mean. And this result is novel, and the counterparts of these results were not previously available in the literature. And this result can be formally stated as provided in the slide. So we can show that for any set of 0 in RD, specifically for TD learning, the P moment of the transient term of the error is bounded by some exponential factor multiplied by norm of theta 0 minus theta star. We can show that the Pollock-Rupert averaged procedure under the assumptions TD1 and TD2 for the step size alpha, which scales as 1 minus gamma divided by logarithm of n divided by delta, is sufficient in order to achieve the error norm in the weighted Euclidean norm associated with sigma phi less than epsilon with high probability by number of iteration given on the slide. So here we see some drawbacks of the vanilla TD0, which potentially can be related with our analysis. Indeed, setting the step size alpha, which is the largest possible one, and which scales as 1 minus gamma, would yield the sample complexity, which is suboptimal by a factor lambda minimum minus 1 in the variance component of the bound. This is the second one. At the same time, setting the step size alpha, which is impractical because it scales with unknown parameter lambda mean, will yield the variance term of the bound, which is optimal, but the bias component of the error, which is suboptimal by a factor lambda minimum minus 1. And this both of these regimes agrees with the previous findings in the literature. So one setting was previously observed by Patil and the co-authors, and the second one was previously observed by Lee and co-authors. So we can also generalize our results for the setting of observations which are generated sequentially and form a Markov chain. In this case, we assume that the sequence of states Sk is really a Markov chain with some transition kernel P pi, which depends upon our evaluating policy pi. And we need to assume that this Markov kernel is uniformly geometrically ergodic. That is, it admits unique invariant distribution, and for any starting state S, it converges exponentially fast to the invariant distribution mu in the total variation distance. And in this case, we propose the modification of TD learning, which is a TD learning procedure with data drop. In this case, we take every observation on the leg Q, where Q is a hyperparameter of the algorithm. And unfortunately, the main problem is that in order to obtain a counterpart of theorem 2, we need that this parameter Q scales with the mixing time of our chain Sk, which is typically unknown in practice. In this case, we can have a sample complexity result which matches the one from theorem 2 up to additional multiplier of Tmix. The proof is based on the Berby coupling lemma and closely follows the ideas introduced in the paper Patil et al. 2023. However, We have also additional square root of log 1 over delta factor in the leading term of this complexity bound as an artifact of applying the construction of Berby lemma. And using Berby lemma construction potentially can be avoided, but in this case, we have to adjust the step size with mixing time to the power -1. And unfortunately, this means that the knowledge of Tmix is still required. So that's all that I wanted to tell in my talk. Thank you very much for your attention.